want to review a little bit all of the physics that I have been cramming at you in the last week. Because I know I take like a month to do what I've covered in just a week here. There's no way that it all stuck. In fact, it's unlikely that much of any. So I want to highlight what was important about that so you can then filter it and get the important things. Start with this funny cartoon again. Okay, so forces. A force is important in astronomy because forces are anything that push or pull. And if it wasn't for forces, we wouldn't have things like things orbiting the Earth orbiting the sun, and so on. Furthermore, we wouldn't have anything that holds the Earth together. So forces, you need to know those are things that push and pull. And of those forces, the one that is most important to us is gravity. Gravity is always attractive, has that equation. Force of gravity is a constant G, mass 1, mass 2 over separation squared. So you had a homework problem that asked about how strong the gravitational pull between you and Jupiter was. Just using that equation, you're able to calculate the answer. And then you're able to calculate how strong it was between you and a semi, and which did you find to be stronger? Jupiter's pull on you or a semi that you're standing next to? Yeah, the semi had the stronger pull on you, which tells you that it's pretty weak at long range. But if you have a big mass like the Earth does, or like the sun does, it becomes a much more significant force. Then we had Newton's 3 laws. The law of inertia says the natural motion of things is just to keep traveling at a constant velocity. That is, same direction, same speed. So if there was no force acting on the moon, it would just travel in a straight line. It wouldn't go around the Earth. So why does the moon go around the Earth? What's the answer to that question? What makes it go around? Yeah, force of gravity. The force of gravity is pulling to the Earth, making it constantly change direction. Newton's second law gives us the relationship between force and acceleration. So we can go through and we can calculate how much acceleration the moon is going to have due to the force of gravity on it. And from doing that calculation, we got two important equations. We had V circular, that is the speed necessary to go in a circle, was the square root of gm over how far you are from the center of the object. And V escape was just square root of 2 gm over r. So using Newton's second law and that force of gravity, we were able to calculate how fast you have to travel to go in a circular orbit, or how fast you have to travel to go and leave an object and not be bound to it. Newton's third law, for every action, there's an equal and opposite reaction. That just says that if the moon is being pulled in toward the Earth, then the Earth is being pulled toward the moon with exactly the same force. And so that's an important aspect to think about. You have a tug of war. You have two teams in the tug of war, and there's a rope between them. Team 1 is pulling on Team 2, Team 2 is pulling on Team 1, and Team 1 wins. Which one is pulling harder on the other team? They're pulling with the same force. And then you say, well, if they're both pulling with the same force, how does Team 1 win? And it's because Team 1 is getting more force from the ground to push them backward than the force of tension from Team 2. Whereas Team 2 is getting less force from the ground than the force that's being applied from Team 1. That's what makes the difference. It's the force you're getting from the ground. So if you have teams of similarly strong people, it's just going to be whichever one has the best traction, which generally comes out to whichever team has the heaviest people is going to win. And that's why the seniors generally have the advantage, because they've grown more than freshmen in tug of war. Then we had the angular momentum stuff. We had angular momentum questions on the homework that was due on Wednesday. And I keep referring back to Alvin because he was the one who came up here and did our demonstration for us, where he had masses in his hand out here. He had what we call a large moment of inertia. Inertia is the propensity to just keep traveling at constant velocity. Moments of inertia is the propensity to rotate at a constant rate. And that moment of inertia is not just about mass, it's where it's positioned. So we had the mass out here, the mass was far away, and you notice I put I is equal to mr squared. So if you have the mass out here, that r squared is a big number, which means you have a big moment of inertia. You bring it in, r squared is much smaller, so I is much smaller. But angular momentum, the rate at which you're rotating, omega is the rate at which you're rotating. Angular momentum is the combination of the rate and your moment of inertia. That's the thing that stays constant. So when you bring the mass in, you have to speed up because your moment of inertia went down to have the same angular momentum. That's another fundamentally important thing in astronomy because it helps us to understand why, for instance, when a star collapses into a neutron star, which is a pulsar, it spins super fast. A pulsar will spin like 1,000 times a second. Do you believe that? You have a star that was much bigger than our sun, collapses, and now spins more than 1,000 times a second. It's also, when it collapses to be about the size of the city of Lincoln. So it's super dense, spinning super fast. And it's spinning super fast because of that conservation of angular momentum. As the mass collapsed, for angular momentum to stay the same, the radius got much smaller, so the rotational rate had to go way up. Then we had light. And so we had two natures of light, the wave nature and the particle nature. The wave nature, an example of where we took advantage of the wave nature, was when we wore those little glasses and we were able to see all the colors spread out. That happens, and I have some slides coming up, actually only like in 2 slides, that tries to illustrate a little bit how that works. But the light is bending around the little slits in the slides, what we call diffractions, diffracting. So light has that wave nature, and that wave nature is where we get wavelengths. You don't have a wavelength without the wave nature. Or you have the particle nature, which says light behaves like particles, like BBs. And those particles have an energy that's proportional to the frequency. So when we, in lab this week, when we talked about the energy spectra, we were talking about electrons that fall from a higher energy state to a lower energy state, and the difference in those states comes out as a particle of light, a photon. Or they can absorb a photon and have an electron go from a low energy to a high energy, but that can only occur if the photon has the same energy as that gap. Right? So these things are all important to astronomy, right? Otherwise we wouldn't go over them. In fact, I was going to make a clicker question about the primary colors of light, and I was, well, actually the primary colors of light isn't important to astronomy. It's important to physics, but not astronomy. So the absorption spectra and the emission spectra are the same frequencies because they have the same energy gaps. It's just electrons going up or down. And now for some relatively new material. That is so well focused. I think it'll come back if I go back and forth maybe. Well, it doesn't matter because this is where I'm going to start doing my show and tell. the have fun play stuff. There, fixed it. So I have here, actually, Alma, can you close the blinds right there? I asked you because you're the farthest back.
Yeah, I'm dying over here.
Poor fella. Thank you. Only the heavier one, which is the back one. Oh yeah, both windows. Yeah, just to make it dark so that people can see us better. So here I have something that's putting out 5 little laser beams, so we can see what happens to light when it hits things. And the first thing I'm going to do is have the light hit a mirror. No, that's not putting in much light. So, obviously this board is not perfectly flat now, is it? Well, we'll ignore this part. I'll work right here. Everybody can see the lines here, right? So I have that light, and I'm going to put my little mirror. Where's the mirrored side? There's the mirrored side. Put my mirror in the way of the light, and now I have the light almost coming straight back on itself. Not quite straight. I can adjust it so it's much closer to straight, or I can put off at an angle, and you see the light getting reflected. Now, if you have a nice flat surface, we have what we call a specular reflection, which you don't need to learn the word specular. You'll just learn mirror-like reflection, right? That's a lot easier to remember. And in that mirror-like reflection, the light comes and bounces off symmetrically about the direction that is what we call normal, perpendicular to the surface of the mirror. So the light comes in, and right now I could draw, there's my normal, perpendicular to the mirror. And so this light comes in, there's the angle of incidence. Incident means coming in. Sorry, apparently some lunch there. And then I have here the angle of reflection, and those two angles have to be the same. That's called the law of reflections. Angle of incidence equals angle of reflection. So if I turn this by an angle of 5 degrees, the reflection is going to change by 10 degrees, because if I change it by 5 degrees, that changes the angle of incidence by 5 degrees, and thus the angle of reflection also have to change by 5 degrees, so it's a total of 10 degree change. So that's how mirrors work. Well, that's nice and simple, right? Can we do anything cool with mirrors? Of course we can. So let's start with this. This is a convex surface. It sticks out toward you. So I put that convex surface here, and the light's spread out. Max, we were talking about the other one, so now I'm going to press you. I haven't talked about anything else. Why is the light spreading out when it hits that convex surface?
Maybe because it's hitting it at all sorts of different angles, and so the light's bouncing off at different angles.
It's all different angles. If we look at the surface normal, here the normal is pointing somewhat up. Here the normal is pointing somewhat down. And so it's going to reflect across that normal by the same amount that it was, same angle. And so if it's more tilted, it's going to spread further. That's not going to work very well for focusing light. Focusing light is bringing it together. So since that doesn't work very well, what shape do you suppose will work very well? Anyone? Convex spreads it out. What will make it come together, converge? Concave. So here's a concave one. So I put the concave mirror here. And you see there, it all comes nicely together. And so we say, we brought it to a focus. The focus is defined, actually the focal point is defined as the place where parallel incident rays, so I have parallel rays coming to that, the place where they all meets the focal point. And so you can focus light with this. They all come to the same place because we have a changing curvature, and now the normal, the farther away you get from the center, the more the normal is pointing back up to the center, and so the more the light gets reflected up there. Now, something that you can't tell with my small optics, this is shaped circularly. And this here, that I'll use in just a moment when I turn the lights back on, is spherical. Spherical is not the right shape. The right shape would be elliptical if we're trying to do something like within the classroom. And if we're trying to do something with astronomy, it's parabolic. So the shape that we actually use for our mirrors is not the right shape, which means there's a little bit of errors in the image due to the shape, what we call spherical aberration, because we're using spherical shape and it's not the correct shape. Now you might ask, why do they use spherical shape if it's the wrong shape? The answer is it's a lot easier to grind things spherically than it is to use the parabolic shape. If you're making the Hubble Space Telescope, you're probably going to do it parabolically. Then again, with Hubble Space Telescope, they put in the wrong shim and they got it wrong right to begin with. Okay, so that's my demonstration up here for mirrors. I'll come back to mirrors in a moment when I'm done with the board. Next thing I'm going to look at is what we call refraction. Refraction is light bending when it goes from a material with one speed of light to a material with another speed of light. Now, a lot of people, when you first hear that, you say, wait a minute. You said the speed of light was constant. Almost. The speed of light in vacuum is constant. If you go into something that's not a vacuum, it can change, but it's always slower than the speed of light in vacuum. So the speed of light in vacuum is constant. It's the fastest speed anything can travel. Speed of light in air is very close to the speed of light in vacuum. For most cases, we pretend that the speed of light in air is the same as the speed of light in vacuum. It's not, and you can tell it's not. How many people have seen a mirage? Or as Bugs Bunny calls it, a mirage? Just Aldwin, apparently. Well, a mirage is caused because you have different temperature air. If it's a bright sunlight day, the air next to the ground gets heated more because you have light being absorbed by the ground, heating up that air. And so that air is hotter. Because it's hotter, the molecules spread out more and light travels faster through it. Because of that difference in speed, light comes down and gets bent and comes back up. So you look down at a distance on the ground and you see the sky instead of the ground. Because light from the sky came down, got bent by the different temperature air, and comes back up to you. So that's what causes a mirage. You're actually seeing the sky. So this here is just a plexiglass bar. Doing good with the language. If I put it in here, nothing happened, right? Utterly disappointing. But if I rotate it, now let's ignore this, that's just reflection. But what's going on inside the rod? It changed direction when it entered the rod, but what's happening when it exits the rod? It changes in the opposite direction. So that this here is parallel to this, but it's shifted because of the refraction, the bending of light when it went through that rod. Now I can make it a little more visible by using a bigger chunk. Although it's hard to avoid, we've got reflections all over the place. And, well, here this is kind of cool actually. The light that's below center is refracted upward. The light that's above center is refracted downward. Why? Because the light is refracted, just like we talked in class on Wednesday. When you go into something that's slower, it bends into it. And so the light is bending toward the center of this block. So if you're up here, it's bent down. If you're down here, it's bent up. And so you can see that the light comes together. Now, this would not make a good lens. It's not going to make all the light come together. This here, we might have some better luck with. But to make a lens work right, well, I'll do it like this first. So I have this flat surface, nothing special happening there. Now, if I bend it, you can see, yes, it goes, it bends toward the normal. But then when it comes to this back curved surface, because of the continually changing angle, it causes the amount that it's bent to vary. Notice these did not all come to focus at the same location. Can you make an educated guess why they didn't come to focus at the same location?
Maybe the surface isn't smooth enough or something?
It's not that it's not smooth enough, it's that it's once again the wrong shape. This is a hemisphere. It's a circular shape. Well, yeah, it's a semicircle because it's two-dimensional set 3. But circle isn't the right shape. It would need to be, for the parallel light, if this had a parabolic shape, then it would all come to focus at the same location. So here is a mirror that is convex, or excuse me, a lens that's convex on both sides. When it goes into the front side, the light is going to bend toward the center because of the curvature. When it comes out, you're going into something faster, which means it does the opposite. Instead of bending into, it bends away from. But because the curvature is the opposite, it'll bend the same way. So it'll do the same thing on both sides. And here we have a nice focusing lens. And so if you use eyeglasses, your eyeglasses are essentially doing that, except for most of us are nearsighted. Is there anyone here who's farsighted? Yeah, it's not very common. So if you're nearsighted, here's what your lens is actually doing. Your lens is spreading that light out. The reason is you can't focus on things that are far away. But if you take this light that's spread out, it looks like the source was just right here, and your eye can focus on that closer thing. That's why we're using this kind of lens to correct our vision. Now for a telescope, we're going to use this kind of lens. And so a telescope is actually made using 2 lenses. That's a mirror. Bad call. Using 2 lenses, and the positions of the lenses are adjusted to make it so you have, and the focal lengths. Okay, you can't even see because of the board not being flat. But this all comes to focus like around here. That's basically how you make a telescope. You have 2 lenses. You need the one out here to have a long focal length. Actually, this one here, that has an infinite focal length. I don't think that, well, no. This has a really long focal length. So I have a really long focal length there. You can see it goes a long ways before it comes together. And then I put out here one with a much shorter focal length. And here we have our final image. What's the purpose of the telescope? It's to make the angle of the light rays bigger so that things look magnified. Now, the angle is like the angle that this makes compared to the angle that makes. It's kind of hard to get the picture from my little diagram, my example. But the purpose of the telescope is to make the angles of the light bigger, and we judge the size by the angles of the light. So if we have light that's coming like this, it's big. Like that, it's small. Wrong ones. So let me now.
Want me to open this up?
You're standing all the time to wait to.
Oh, I didn't sleep last night, so if I sat down, I would have fell asleep. I promise you that.
Okay. No, go ahead and leave. There's no point in opening them.
Okay, because I almost fell asleep standing up right there.
So here I have a convex and a concave mirror. Which one of these did we say would be useful for a telescope?
Concave.
The concave. The concave is the one that's useful for the telescope because when the light rays come in, if you have parallel rays coming in, they're going to come together to a focus. This one here, the convex, if parallel rays come in, they're going to spread out. Not focused, not very useful. Now, if you look at this, it has definite uses. Like, have you ever seen one of these on the side of a road? What's the purpose? So you can see what's around the corner. We used to have one right over here before they closed that road because you have a sharp turn, people come flying by, 30 miles an hour. If somebody's coming the other direction, you don't have any warning. So they put something like this there, so somebody coming in like here can see that there's a car over there. This allows you to see a large angle because of the way it spreads out the light. So that's a usefulness. If you look at the rear view mirror in some cars, you'll say, objects are closer than they appear because they're using something like that. So this here is what's useful for our telescopes. So if we're going to make a reflecting telescope, we'll use something like this as the primary mirror. So parallel rays come in here, go toward the center. Now things that are really cool to notice with this. If you look at yourself, so Connor, can you see yourself in this?
I can.
Okay. How would you describe the image you see of yourself?
I am upside down.
Upside down. And are you larger or smaller? That is, do you look like you're magnified or diminished in size?
Diminished.
Okay? So upside down, diminished. Now I'm going to bring it closer. So what's happening as I get closer? You see yourself?
I do.
What do you look like?
A lot more focused and I'm all the way over at that.
Okay, that would be my angle. Which way should I turn? Have you grown? Has the image grown or got
Yes.
smaller? So getting bigger, are you still upside down or?
Yes.
Okay, coming closer. Now what do you see?
Everything's just kind of. But if I throw my arm in there, it's like
Okay,
magnified.
do you see your face still?
No.
No. I call that the meat pie look. If you get the right distance away, what happens is it's making an image behind your head. Well, if the image is behind your head, you can't focus behind your head. And so everything's just blurry. Now, if I get even closer, now what do you see?
So,
And is it inverted?
no.
It's not inverted now. Don't lie to parents. And is it bigger or smaller?
Oh, it is so big.
It's so big, and now it's upright. The type of image you see depends on your distance because when this is far away from you, it's going to make an image that's, light comes from you, like this, it makes an image like right here, and then the light goes across itself, and so you're seeing it inverted, and you're seeing an image like here. As you get closer to you, the image moves farther from this, and so we can get to the position where the image is behind your head and you couldn't see it. You just saw a blur. Then you get even closer, and you actually create a virtual image back here that's bigger. Virtual means the light rays weren't where you saw the image. So it's kind of fun to play with these, but this is the fundamental piece that we use in our telescopes. Now I'm going to put a couple more things on here for telescopes. For a telescope, for a Galilean telescope. Galilean telescope is a simple telescope that's a refractor with two lenses. The length of the telescope actually has to be a specified length because you have two lenses. An object is way out here. Here's your object. And so the lens that's closest to the object, we call the objective. Objective because it's facing the object. It's actually obvious if you know why it's called objective. So the objective lens has to have a long focal length. And then you have one that's next to your eye, and hence you call it the eyepiece. So right behind that eyepiece, you have your eye. And the eyepiece has to have a very short focal length. And the way we actually set these up is you have the separation between the two lenses is the sum of the two focal lengths. So the length has to be just the sum as illustrated in my picture. But the thing that people worry about, of course, is the magnification of the telescope. The magnification is minus the focal length of the objective over the focal length of the eyepiece. So that's why you want a long focal length of the objective. That increases your magnification. A short focal length of the eyepiece increases the magnification. The minus sign is because just like with what Connor saw, you have an inverted image from this telescope. Now that inverted image makes it a little odd when you're trying to use the telescope. If you are trying to aim at the moon, and you see the moon is a little to the right in the telescope, you actually need to move the telescope to the left because it's inverted. So usually when you're looking at a telescope, you don't look up at the moon or anything. You just look at the telescope and you adjust the telescope and look at how the picture moves. Don't pay attention. But if you were paying attention, it'd be confusing. If you're trying to watch a football game using a telescope, oh, the guy's running to the right. Well, that means I have to turn to the left with my telescope to keep him in the telescope. We'd get confused. But for looking at distant stars and whatnot, we can't see it, so why would we care? But these are important equations, the magnification and the length. Now, I know I had slides on these, but I couldn't find them when I was preparing today's lecture. If you go to buy a telescope, it's probably like in my second to last slide or something, I just didn't see it. If you go to buy a telescope, you want to get one for fun. I've already told you what's the most important thing to look for in buying a telescope. Size. Bigger is better. 2 slides from now, we have the explanation of why bigger is better with regards to resolution. Previously, we already had the equation that the light gathering power is proportional to the radius squared, or the diameter squared, whichever way you want to look at it. So the bigger it is, the more light it will gather, hence the fainter things you'll be able to see, and you'll be able to get better resolution with it. So size, you want to buy the biggest telescope you can get. What's the other important factor? Okay, it's the quality of the lenses. You don't want cheap plastic lenses, you want quality ground lenses. If you have a large telescope with quality lenses, you'll have a good experience. Unless it's out of alignment. And trust me, aligning a telescope is harder than I want to ever do. I don't know if you've watched that crazy, ludicrous movie, A Walk to Remember. In that movie, this guy who, could barely pass the driver's license test, it seems, puts together this telescope and it magically focuses. It takes a lot of work. And then it has to fight. How many people see that movie? I watched it, and you get to the payoff scene, and I started laughing. I got angry. Because then the girl who dream has been to look at this comet looks into the telescope, and you see when she gets to it, she bumps it, and it physically moves. Well, with the telescope, when you bump it, even if you can't tell it moved enough that you're seeing something completely different in the sky. If you can see that it moved, nowhere close to where it was aimed initially. But that's okay, because she looks in and she still sees the comet. And the comet you see going something like this across the sky. No, you don't see any kind of motion with a comet. It was really, really humorous. One other thing is, if the comet is a major comet, you're best off viewing with binoculars or less. If it's a very distant, faint comet, then you'd use a telescope. So, using a telescope is overkill for most comets. When Halley's Comet comes around, you can just go out there with your bare eyes and you can see the comet filling a quarter of the sky. By the way, all of this reminds me, anybody know what's happening right this very minute? Well, it peaked a half hour ago. A penumbral lunar eclipse. Now, it's only visible. Should we run out and look for the penumbral lunar eclipse? It's going to be going on for another hour or so. What time of day is it? I don't know, but it ain't nighttime. Lunar eclipses can be seen anywhere in the world as long as it's nighttime. We're not in nighttime, so we can't see it. We're on the wrong side of the earth to see it. But then again, it's a penumbral eclipse. Do you remember the word penumbra?
Doesn't it mean like not the main shadow, but kind of the side?
Yes.
Shadow?
It's the region that's partially shadowed. Well, that means a penumbral eclipse means the moon is passing through partial shadow, which means it's getting hit by light, just not as much as normal. So what does a penumbral eclipse look like? Maybe a little bit orangish, but it still looks like a normal moon for the most part. So penumbral eclipse, really unexciting, but we can't see it anyway. What phase does the moon have to be if we're having a lunar eclipse? Last night when I was driving home for a brief period of time, the sky was clear and I saw the moon. I was like, wow, that is a beautiful full moon. Because when you have a lunar eclipse, the Earth had to pass between the moon and the sun. And of course, since we're having eclipse, we know we're in eclipse season, which means that the moon is crossing the ecliptic right now. All right. So that was, well, it was mostly review, although I hope you learned a lot of new stuff, especially about the lenses, because I actually showed you how they work. The lenses, we're not going to work with optics in this class, but once again, having just some knowledge of how the telescope works. It's not magic. If you go back to Galileo, didn't invent the telescope, but he was the first one to use it to systematically study the skies. And some people refused to look through that telescope because they said that telescope will bewitch me. It will be, I could see my mother saying these words, it's a tool of the devil to deceive me. It will show me what's not really there. There were people who refused to look through the telescope because they didn't want to give the devil an opening to deceive them. And so I want people to understand the good reasons behind how a telescope works so you can understand, okay, so it's a reliable instrument. What we're seeing is what's out there. It's the interpretations that we have to be careful with. All right. This picture here is actually showing water waves. It's not light waves, water waves. But you see water waves and see these straight lines going across. Those are because you have places where the water goes high, low, and the light refracts at different angles because of the different angles for the water surface. And the light refracting at different angles is what gives you regions that are dark where it's not refracting toward you, regions where it's bright where it is refracting toward you. And so what we can see with those ridges is what we call the wave fronts, where we have the peaks of our waves. And so each time you see a white light, think of that as the peak of a wave. And so we have these waves that are coming down just like planes, called plane waves, hits that hole, but when it goes through the hole, it doesn't go through as a plane wave. How would you describe the shape of the wave once it goes through the hole? This shape here. There's lots of words for that shape. Any one of them will do. Curved, okay? Curved works for me. It's curved. The light didn't stay going in the same direction. We always tend to think light goes in one direction. When light goes past an obstruction, it will bend. And so you have some light that's coming out this way, some that's going this way, some that's going this way. Whereas before, all of the light was going straight down. So we call this bending of the light when it goes through an opening or around the barrier, diffraction. That's what the glasses we wore were using, that diffraction. So that diffraction allowed us to spread out the light because in those glasses, we had multiple holes. So I'm trying to draw holes here with the green. And so that meant that the light coming through spread out like this. And so there are places where they come together and they're exactly one wavelength out of the path lengths are one wavelength different or two wavelengths different. And they add together to give you a brighter light. There are other places where they come together, and it's like a half wavelength out, which means one wave was at its peak. So one wave's like this, and the other wave is like this. When they come together, they just add up, and that would add up to 0. And so you get places where they add up to 0, places where they add up to really big. And those just alternate. So if you look out here, you would see a pattern that goes like this. Well, it's actually the exact reverse of what I just did. Start in the middle. A pattern goes like that with multiple places where it's bright. So bright where I'm drawing these dots. And multiple places where you have no light where I'm putting the black dots. And so that's what our glasses were doing. Where it was bright is where we saw the colors. For different colors, it was different angles where we had this. So we saw different colors bright at different locations. It spread them out. Well, why is this important here? Well, this diffraction occurs anytime you have a border or an obstruction. So if I have my mirror here, or if I have a lens, I have a border on the mirror. And so I'm going to have light bending because of the border. The bigger the mirror or the bigger the lens, the smaller that effect's going to be. So the actual angle for the resolution is given by this equation if you have a circular opening. So that angle is a measurement of the smallest angle that you can resolve. Resolve means that you can see the difference. You can see a detail that small. So the smaller that angle, the better the details are you can see, the smaller details you can see. Hence, good resolution is a tiny angle. Bad resolution is a big angle. And so you see that resolution is proportional to the wavelength. So shorter wavelengths, better resolution. Longer wavelengths, worse resolution. Hence, we talked about radio waves. Are radio waves long or short wavelength? They're long. They're very long. Somewhere between, man, everybody's sleepy. I have a bunch of yawners, a bunch of nodders. Radio waves are really long, like 1 meter to a kilometer. And so with those really long lengths, your angle for resolution is going to be a large angle, which means you can't see much fine detail. That's why when we looked at a picture of the radio wave picture it was the Crab Nebula, there wasn't much detail there. It was just kind of a big blocky thing. Well, we can kind of counter that because it's divided by the diameter. So if I have a bigger opening, remember the Arecibo telescope is more than 300 meters across, then that's going to make the resolution angle smaller, which is better. But that in itself is not good enough. We'll see on the next slide how we deal with that. But let's go to another band. Let's say we go from radio waves to visible light. What's the wavelength of visible light? 400 to 750 nanometers. 400 to 750 nanometers. I mean, I can hold my fingers together and say that's 400 nanometers, right? It's very, very tiny. So going from a meter to 400 nanometers, your resolution for the same size opening would be like a million times better with visible light than it is with radio waves. So we can get away with a much smaller telescope because we have such a short wavelength. If you're using a microscope, looking at some little insect, you might want better resolution, and so you try to go to a shorter wavelength. So you go to blue. They'll make microscopes that use blue light because that's the shortest visible light. It'll give you the best resolution. Some microscopes, they actually submerge them in oil because oil makes the wavelength even shorter so you can see more detail. All right. Our first clicker question. Give me a second here to press the button. Oh, Craig. I think I can change this later. I have you guys. Actually, I don't know if anyone's answered or if it's me, so don't answer now. I'm changing things. I had it set for the wrong class. None of you guys are in general physics. Okay, now you can answer. What does resolution of a telescope mean? What does it tell us? And right now, Yari's the only answer in case other people think they've answered and it wasn't responding yet. Okay. We had 1, and at the last second, somebody changed to 10. So, this person here, Tioni, give us your answer and your reasoning.
Listening to what you said, probably D,
Mm-hmm.
because you said it's the quality of what you can see. So that's not at least the amount of detail.
Okay.
I picked it wrong a little bit.
So if it's the amount of detail, is it better to have a small angle or a large angle?
Small answer.
Small angle. That seems counterintuitive, so that's why I asked the question to make sure we seal in. Better resolution means a smaller angle. And so it gets confusing because you like to say, well, it's got a larger resolution. Well, the word larger would imply that it's a larger angle and that's a worse resolution, so you have to be careful with your words. All right, here is how we can improve the resolution for something like a radio telescope. For the radio telescope, because you have such a long wavelength, even something the size of the Arecibo telescope, just take the ratio of wavelength over diameter. For visible light, you typically have something that's like 14 inches in diameter and light that's this big. For radio waves, you can have a telescope that's 300 meters in diameter for light that's 300 meters in diameter. That's just a 1-to-1 ratio instead of hundreds to 1. So your resolution, even with a super big telescope, is just never going to be good with radio telescopes. So what they do is they use an array of telescopes. It can be an array of 2, but they use multiple telescopes and then they combine the image. Interferometry means we're taking the images from multiple things and we're putting them together and seeing how they add together. We call that interfering when they add together. And by doing that interferometry, you can get a resolution that's equivalent to what it would have been if it was the separation. And so here is an example of the improvement in resolution for a radio telescope using one telescope and using an array of telescopes and interferometry. And in this picture on the left, that looks like one object. The picture on the right, you clearly see that there are 2 objects there. Okay, we're going to have to end here with talking about the Earth's atmosphere and how that affects our astronomy. This picture here shows the transmission of light through the Earth's atmosphere. If the line is at the bottom, that means that electromagnetic radiation goes right through. If it's at the top, nothing gets through. So if you look there is a nice big region where electromagnetic radiation goes right through. What range is that in? In which one? The radio. So we call it the radio window. Radio telescopes have clear viewing of the sky. You go over, there is a very small infrared window, but it's a small fraction. Then there's the visible light window. That's pretty good. If you look at that, now, I believe that God created us. So I believe that God created us so that the range of light we see is a range that goes through the atmosphere. If we had vision that was over the ultraviolet, we couldn't see the stars because it'd be blocked by the atmosphere. If we had vision that was down there in the infrared, we couldn't see the stars. It'd be blocked by the atmosphere. if you're evolutionary minded, you might think that, well, vision randomly had a selective advantage. But I would say no. This vision would have a selective advantage. That if we're a predator-prey model, the selective advantage would be in the infrared. Not quite as acute vision, but you don't have to be in daytime to see anything. Right? If we had infrared vision, we could walk around at night and we could say, there's a tiger, I'm staying away from him. But with our visible light, we don't have that ability. So I believe that God created so we can see out of the atmosphere and appreciate the heavens above that I believe declare the glory of God. Okay, we'll stop here.